Good morning, students. Today we will study a very important thing, that is divergence of a vector. Okay. Now what is a divergence of a vector? Definition wise, divergence of a vector A at a given point is the outward flux per unit volume as the volume shrinks about the point P. Divergence simply means flux coming out of a point or going into a point. Okay, suppose there is a point P and the flux lines are coming out of that point. Suppose like this. Then we say that this is a source point and the divergence is positive. We say it is positive divergence. For example, a balloon and inside which air is there, okay, and you make a small hole on it. So what will happen? The gas will come out. So that is positive divergence. Divergence means flux lines coming out of a point. Or suppose flux lines are going to a point P like this. Then we say that the divergence is negative and the point is a sink point. Sink and divergence is negative. Suppose I am taking another thing. For example, there is a point and some field lines are going out from this point, and some flux lines are going towards this point. So the net divergence is 0. Net divergence is 0 at this point. Okay. So definition wise, divergence of a vector del dot A is equal to the outward flux. Now flux is what I can write, flux density into surface, closed surface. So that is flux per unit volume, where the volume shrinks to 0. That is, volume shrinks to a point. Then the outward or inward flux, the field lines coming out or coming towards the point, is called the divergence of the vector. Okay. Next point is divergence theorem. Now what is divergence theorem? Gauss-Ostrogatsky theorem it is also called. Okay. So divergence theorem relates surface integral of a vector with the divergence of volume integral of that vector. It states that divergence theorem states that the surface integration of a vector is equal to the divergence of the volume integral of that vector. According to the definition, the total outward flux of a vector field A through the closed surface S is the same as the volume integral of the divergence of A. Means surface integral is equal to volume integral of the divergence of A. For proving this theorem, what I will do, I will consider a surface. This is a surface, means this is a surface enclosed by a volume. Consider this is a volume. Okay, now I have divided the each volume into, let k cell, into k cell, k number of number of cells I have divided this volume. So each volume is del vk. Let like this volume is del vk. This is one part of this whole thing. Okay, and the surface is, let it be del sk. Total surface is sk, total volume is vk. I have divided into small k cells, so each cell is del vk, and considering the surface as del sk. Okay, so what I can write? I can write that the total surface is A dot ds is equal to how much? this is equal to that small surface, that small surfaces. So I can write, I have divided into k cells, so summation of k into, I will just write according to sk. So del of sk is that small surface, okay, into a dot ds. Okay, is it okay? Now divide and multiply by del vk. So this is k sk a dot ds multiply by del vk and also divide by del vk. Okay, vk is the volume of that small surface. Clear? Now taking the limit, what you will get? Let, I am writing this way, limit del vk tends to 0, small surface a dot ds divided by del vk into vk. Now according to the divergence definition of the divergence, limit del vk tends to 0 and this closed surface area a dot vs by del vk, this is what? This is nothing, this whole thing, this to this whole thing is nothing but divergence of a, isn't it? So I can write it as summation of k, and this is nothing but divergence of a into del vk. Okay, now what is this? Summation of k del dot a into del vk, this is what? This is volume integration. Summation is integration, so integration, volume integration of del dot a, and instead of del vk I can write dv. Therefore what we have obtained is closed surface integral of a dot ds is actually equal to del dot a into dv. And physically also, when we divide the volume into small volumes, then inside the volume actually the net divergence is 0 inside the volume. It only remains only at the surface, because inside the volume the net lines of forces for one volume is inside and for another volume it is outside. So inside and outside will cancel. Only it remains at the surface. So surface integration is actually divergence of the volume integration. Hence it is proved. Thank you.